Okay, again, we're going to look at this on the paper and not on the boards just because I'm videotaping. So I noticed I had slightly different numbers when I was working this, and I think I must have had a different K chart. So we have sodium sulfite makes sodium ions and sulfite ions. So the first equilibrium controls the pH. Sulfite plus water gives us hydrogen sulfite plus hydroxide. 0.2 molar, 0, 0, minus X, X, and X, and 0.2 minus X, X, and X. Now, we need a Kb value for the sulfite ion. So that's calculated by taking Kw divided by Ka2. When I looked this up when I was doing this, I got a Ka2 value of 6.6 times 10 to the negative eighth. When I look up here, I see that you got the number in your chart as 6.3 times 10 to the negative eighth. So my answer is going to be a little bit different. Don't get all worked up about that right now. We're looking at the process, and I'll make sure that on a test we all have the same chart. So that gave me a Kb of 1.5 times 10 to the negative seventh. So I plug that in. It's equal to X times X divided by 2. Rearranging and solving for X, X represents hydroxide, 1.7 times 10 to the negative fourth molar. So the pOH is 3.77, and my pH was 10.23. And if you use the numbers from your book, your pOH was 3.75, and your pH was 10.25. And we had one group that truncated. Remember, watch your sig figs when you're subtracting. Okay. Any questions on salts of diprotic acids? Okay. Now we're going to look at the pH when we're doing a titration. And this gets really awesome because it gets really complicated. And this is not about what you want here. Where did you see in the course description, Chem 112 is what you want? It doesn't say that. It says you're going to learn all about pH. The more we move forward today, the more time we have to practice before the next test, and that's really important. Trying to figure out what the heck is in that beaker. What's controlling the pH? Okay. So, we've done titrations. And in lab on Thursday, you're going to do a titration. So, a titration is defined as a reaction done in solution. We measure the amounts by volume of the reactants added. We talk about the equivalence point in an acid-base titration. And the equivalence point is where we want to stop. And that is where we have stoichiometric equivalent amounts of the acid and base. We're done because we have equal amounts. The end point is where we stop doing a titration, an acid-base titration, because we stop there because our indicator changes colors. Now, you've titrated with phenolphthalein. And remember, when we titrate with phenolphthalein, we're going from an acidic pH to a basic pH. We go from colorless to pink. And phenolphthalein, you use this in Chem 111. And you were instructed to look for that first very faint tinge of pink, where it's just barely pink. But some of you have a heavy hand on the stopcock and you got pink, right? And it's usually only one drop between pink and pink. So we stop at the end point. And we want the end point to be close to the equivalence point. Most of the time it is. And we have different indicators. They change colors at different pHs. So until now, we've just kind of thrown them in there and titrated. Now we're going to look at the calculations about why is it changing color and what's going on in my beaker. So a titration has 4 different zones. we put something in the Erlenmeyer flask, we can calculate the pH of what's in the flask before we start titrating. Then we titrate and we're at the equivalence point. Then we reach the equivalence point. Then if we keep dumping in titrant, we go beyond the equivalence point. And we can figure out the pH at any of those positions. Now, you remember from your introductory classes that in quick and dirty terms, acid plus a base, when we're titrating, an acid-base titration, yields a salt plus water. Anybody remember hearing that in your introductory chem? Acid plus base yields a salt plus water. Well, the cool thing about not being in intro chem anymore and being in Chem 112 is we now know that salts can be pH neutral, like sodium chloride, so the pH at the equivalence point would be 7, or those salts can have pH activity. So now when you've finished your titration and you've made a salt, that salt can have an acid, conjugate acid of a weak base, cation, that makes it acidic, or it can have a conjugate base of a weak acid anion, which will make it basic, so your pH isn't always neutral. And we're going to look at how to calculate that in all sorts of situations. It's really cool chemistry. It really is. The math, you've been doing the math. The problem is you got to figure out how to figure out what the heck do I set up for my ice chart. But you know how to do the math. So, the acids and bases can be strong or weak. And when we combine them, then we get different mathematical calculations for each one. So, we'll start with the easiest. The easiest is strong acid, strong base. Because when you have a strong acid and a strong base, the salt usually contains some kind of metal cation that doesn't affect pH, and then it contains the conjugate base of a strong acid which doesn't affect the pH. So when you're at the equivalence point, the pH is 7. And before the equivalence point, you have neutralized some of the acid or some of the base, and you have to figure out what's left over in my beaker. Now, what's in my beaker, and what's the concentration of that thing in my beaker, and what's the pH? So it gets real fancy compared to when we just started out calculating the pH of a strong acid or a strong base. Okay, let's look at this example. We're titrating 50 milliliters of 0.1 molar HCl with 0.1 molar sodium hydroxide. So the very first thing that you do is you look at this and you say, well, what's the chemistry going on? I'm titrating HCl with sodium hydroxide. Now we say to ourselves, what is this acid-base speaking? Well, it's a strong acid, and I know that because it's one of the 7 on my list. What is this? A strong base, and I know that because it contains the hydroxide ion. So, acid-base titrations are double replacement chemistry. Back to chapter 4 or 5 in Chem 111. I trade partners at the dance. NaCl plus H2O. Some of you who didn't have me, there's a good 80% chance that your instructor used that analogy, right, of trading partners at the dance? No? Your instructors didn't dance? Okay, well, can you picture that? Okay, I'm dancing with Taro. Megan's dancing with Brady. All of a sudden, we stop and we trade. I grab Brady, she grabs Taro, and we dance away, right? We traded partners. So, the hydrogen was hooked up with chloride, sodium was hooked up with hydroxide, we traded partners. Now, sodium and chloride are hooked up, and hydrogen and hydroxide. Okay, so we're trading partners. So now, before any titrant is added, what's in my beaker? Well, I have 50 milliliters of 0.1 molar HCl in my beaker. So in the beaker, I have 0.1 molar HCl. This is the first kind of pH problem we ever tried when we introduced pH. So the pH of this is minus the log of 0.1 molar. So the pH is 1.000 because that HCl breaks apart completely and gives hydrogen ions and chloride ions. So I have a strong acid and I'm taking the pH, yes. Does volume matter? If I have 50 mils of 0.1 molar hydrochloric acid, is it going to have the same pH as 500 mils? Yeah, so the volume doesn't matter. Not at this point.